Okay, I think we'll go ahead and get started. I'm Saman Razavi. Jeff McDonald and I would like to welcome you to the sixth seminar of this year's seminar series on breakthroughs in water security research. Next week, we are going to have Jim Hall from the School of Geography and the Environment at the University of Oxford. As always, we'd like to thank Howard Tweeter, Canada Excellence Research Chair and the Director of Global Institute for Water Security for underwriting this seminar series. This week, it's a pleasure to welcome Chris Soulsby to Saskatoon. Chris is a professor of hydrology at the School of Geosciences at the University of Aberdeen, Scotland. He received his PhD in geography from the University of Wales in 1991. In 1993, he joined the faculty of the University of Aberdeen, and since 1999, he has been a full professor there. Chris is a founding member and the director of the Northern Rivers Institute, a center of research excellence for environmental hydrology. He has been a leader in isotope hydrology, eco-hydrology, and shallow groundwater surface water interactions, with a particular emphasis on tracer-aided modeling. And I believe that's what we're going to hear about today. Chris has been highly involved with editorial activities as he's on the editorial boards of leading journals, such as Hydrological Processes, Journal of Hydrology, and HESS, the Hydrology and Air System Sciences. He has several leadership roles in different initiatives. Just to name a few, he's been the theme leader in process conceptualization of the POB initiative, Prediction in Engaged Basins of the International Association of Hydrological Sciences, or IHS, and vice president of the International Commission on Tracers of IHS. Chris is a fellow of American Geophysical Union, AGU, for his fundamental contributions to understanding runoff generation. Well, it's a real pleasure to have Chris here today. Chris, the floor is yours.
Well, thanks for the generous words, Saman, and thanks everybody for coming along. And thanks to Jeff and Howard and the Global Institute for inviting me to come over and take part in this distinguished lecturer series. It's a great honor to join the esteemed folk who've spoken in this series before me. And it's been fantastic to visit Saskatoon for the last week and interact with many of you. It's been a great... It's been very intellectually stimulating to be here, and it's been great to be in Saskatoon. So, as Saman said, what I want to talk about today is about breakthroughs in tracer-aided hydrological modeling. That's been something that's occupied much of my research activity for the last 25 years or so. And the kind of environments that typically we've been working in is in the Scottish Highlands, and I just put this on the opening slide to give you a kind of feel for the sort of landscapes that we've been working in. Fortunately, I've been privileged to work with a lot of really great people in terms of this tracer-aided modeling, in particular former postdoc Christian Burkle and Dirta Tetzlaff. Together, we've been involved in collaborations on tracer-aided modeling for almost a decade now. And I'll also today talk about work that's been done by more recent postdocs, Marilyn van Hoogevor, who's now at Princeton, and Pertti Ala-Aho, who's a postdoc with us at Aberdeen at the present time. So I acknowledge these contributions from my colleagues. So as an outline of what I want to cover today, I just want to give some background to tracer-aided models, what they are and why I think they're useful. To talk about some of the breakthroughs, particularly in the work that we've been doing in Scotland in use of conceptual tracer-aided models, and to talk about the potential of more physically based tracer-aided models in the future, and the application of these models in applied situations to lead on to some comments about the outlooks for research activities over the next few years. So to go back to the background of tracer-aided model, I guess my kind of locus for interest goes back to the scientific stone age of the late 1980s when I was a PhD student at the University of Wales. And a paper was produced by Colin Neal and others that had the unwieldy title of Chloride in Precipitation and Stream Water, for the upland catchment of River Severn, mid-Wales, some consequences for hydrochemical models. And it's an unwieldy title and it's very understated, but this consequences for hydrochemical models is quite profound and really stimulated a lot of interest in tracer hydrology, which led to the classic data sets that have been collected at Plinlim and analysed by people like Jim Kirshner. But going back to the start of things, the core interest that Colin and others had at the Plinlim and catchments was looking at upland afforested catchments and the phenomenon of acidification. This goes back to the acid rain days of the 1980s, and they were particularly interested in hydrological events or stream flow responses, which are very flashy in upland catchments in Wales, which caused near-surface hydrological pathways to bring acidic runoff. This is hydrogen ion activity here, which also mobilized high concentrations of aluminium and led to the ecological degradation of these upland streams and loss of salmonid fish species. So there was a lot of interest in the acid rain days in the first kind of generation of hydrochemical models that explicitly linked hydrological modeling to biogeochemical processes and water quality predictions. And the work that the modelers in these early days of acidification carried out basically looked at very sort of simple kind of conceptual hydrological models, a kind of model with a soil store and a groundwater store that could route the acidic runoff into the streams and the more alkaline base flow and mix them up and predict not only stream flows, but predict the aluminium and acidity of stream waters. And Colin Neal, being quite an iconoclastic figure and quite skeptical of the early generations of hydrochemical models, said, well, if these models are so great, we acknowledge that they can simulate stream flow really well, but as well as that, if they work really well hydrochemically, they should be able to take a conservative tracer, and he used chloride in precipitation, which is highly variable in the uplands of mid-Wales. He could have used an isotope as well as an indicator of variable rainfall inputs. But unlike the variable tracer signal coming in rainfall, if you routed that tracer through the hydrochemical model, it actually spectacularly failed to produce the damping and lagging of the rainwater signal that you saw in stream water. So whilst the stream water signal is relatively damped compared to precipitation, the modeled response was highly variable and didn't get anywhere near close to predicting what we measured in stream flow. So this showed that the model, in terms of, although it was able to simulate stream flows pretty well, it failed to characterize the storages within the catchment because it couldn't damp the tracer. It couldn't conceptualize the mixing processes that led to this damping, and therefore it couldn't represent the flow paths and fluxes very accurately. And so the fact that it could simulate pH and aluminium was more of an artifact of the model architecture and then being co-correlated with runoff rather than the model doing anything smart itself. So this led to a reappraisal of these kind of hydrochemical models and the need to get the right answer for the right reasons, that the hydrological processes had to be accurately parameterized within hydrochemical models if you're to simulate water quality properly. And the same is true if you're using a hydrological model, say, for predicting the effects of land use change. You need to know where the storages are, what the fluxes are, and the mixing relationships to be able to do that properly. And since those days, a lot of work has subsequently gone on with tracer-aided models, and collection of data sets has exploded, especially in terms of using isotopes with new technologies that are available. But a recent paper that Jeff and Keith Bevan did in Water Resources Research last year still identified a grand challenge, the ability of hydrological models, not just to be able to model the input-output celerity transformation within the runoff response that most hydrological models could do, but also to be able to capture the residence time distribution of water contributing to the stream hydrological response, which moves at a completely different velocity compared to the celerity of the stream water response. So despite a lot of work, Keith and Jeff identified this as a major challenge for hydrology at the present time. And last year also, Christian Burkle and myself did a review paper on the kind of history of tracer-rated rainfall runoff models, but one that was also forward-looking in terms of calling for a utilization of these models to realize their potential in the future. So that's what I want to cover, or that's the background of today's talk. And over the last 10 years or so, we've done a lot of work in the Scottish Highlands trying to develop these trace-rated models to understand catchment hydrology better. The site where we work is a place called the Gurnock Burn. Burn's just a Scottish word meaning stream. So it's a 30 square kilometre upland catchment. The geology's granite. It gets about 1,000 millimetres a year of precipitation. And it's connected to the River Dee, which is a large river system in the northeast of Scotland, which drains into the North Sea. Now, the reason that we work in this catchment is that it's a long-term study site for Atlantic salmon. So fisheries biologists since 1966 have been working in this catchment, studying salmon populations. And salmon they're born and spend their juvenile phase of their life in freshwater streams like the Gurnock Burn. Then they go out via the River Dee into the ocean. They spend several years in the North Atlantic growing and come back as large fish to spawn in the same stream and produce the next generation of fish. And the fisheries biologists recognize that there's a strong hydrological influence on virtually all the phases of the salmon life cycle. And we started working with our colleagues at Marine Scotland Science to look at these hydrological interactions. But that forced us to look back not just at the hydrology of the stream, but the hydrology of the landscape and how the landscape was connected to the riverscape. And that involved us looking more closely at the fundamental hydrological processes that are going on in these catchments and trying to use traces and models to understand them more comprehensively. So this is a kind of another perspective across the catchment landscapes where we're working, and it shows their general characteristics quite nicely. It's a glaciated landscape, so the valleys tend to be over-widened and over-deepened, and they're full of glacial drift. So in the valley bottoms, where you see these kind of pale yellow areas, where the gradient's low, we tend to have peaty soils, which can be anywhere between about 0.5 metre to a couple of metres deep. The peat has low permeability. It's formed on low permeability glacial drift. And these soils are very responsive. They generate runoff via saturation overland flow, shallow subsurface storm flow. In contrast, on the more steeper sloping hillsides, the better drainage has resulted in more freely draining podzolic soils being the dominant soil type. And these soils are more characterized by vertical drainage to groundwater recharge or perhaps deeper subsurface flows towards the stream channel. So we've been quite successful in just, even before we started any modeling, just being able to conceptualize the dominant runoff processes in a catchment landscape like this. When we wanted to go and do some more detailed measurements, obviously 30 square kilometers is a big scale to operate at. So we focused on a 3 square kilometer subcatchment of the Gurnock called the Bruntland Burn. And this was quite convenient because it was at the bottom end of the Gurnock catchment, but in many ways it was a kind of miniature replica of the Gurnock. It had 20% of the lower catchment, this is showing it in plan view here, is characterized by these peaty soils. It's got the steeper podsols characterizing most of the rest of the catchment and some kind of thin regosols on the catchment interfluves. And at the site, starting in 2003, we started to collect isotope data as a tracer. So we collected daily precipitation time series of isotopes coming into the catchment. We measured daily isotopes in stream runoff. And increasingly, as time's gone on, we've extended our study. We monitored a representative hill slope transect, going from the peaty valley bottoms to the upper catchment hill slopes. We've also monitored other soil water sites around the catchment, distributed a range of groundwater wells in the catchment, which Chris Gabrielli, who's here, helped us drill a couple of years ago and had great fun doing it. And we've had synoptic surveys of water samples from the stream and the wetlands in the valley bottoms. So we've collected a very rich data set from this catchment in terms of isotope systematics. We've also monitored soil waters and groundwaters for isotopes as well as looking at them hydrometrically. And the philosophy behind this experimental design was to use the isotopes to understand the flow paths at the plot scale, down individual soil profiles, at the hill slope scale, and then at the catchment scale. and hopefully integrating all of this tracer data together with models to test hypotheses about runoff processes at different spatial and temporal scales. So the isotopes was built into the experimental design of the catchment right from the start. And so to think about building up a perceptual model as a basis for mathematical models of runoff responses in this catchment, first of all, we need to think about the dynamics of the surface flow processes. And this catchment, the runoff response, is largely generated from saturated areas in the peat soils in the valley bottoms. But in the dry conditions, the saturated area is really quite limited in its spatial extent, just a few % of the catchment. But when the catchment is wet and the hill slopes connect to the riparian wetlands, the saturation zone can occupy up to 40% of the catchment. And this dynamic regulates or controls the nonlinear response of stream flows during storm events. In contrast, we also have quite large amounts of water stored in groundwater, so we need to think about the deeper subsurface flow processes in the catchment. The bedrock in the catchment is characterized by granite, so it's relatively impermeable. But in the valley bottoms, there's quite extensive thicknesses of glacial drift, up to 40 meters deep. And we know this because we've taken some transects across the catchment where we've done geophysics. And with the geophysics, using resistivity surveys, we can identify the drier, impermeable areas as high resistivity, where electricity can't be transmitted, with the less resistive areas, which are usually indicative of water saturation. And simply put, the bedrock is about, in the valley bottom, it's about 20 to 30 meters deep, providing a no-flow boundary. In the upper surfaces, the peat soils and the underlying drift is saturated. And then this dries as we go up the hill slopes, though in some places we can see more saturated groundwater wedges, which are gradually, slowly migrating down to the stream. So we've got a lot of water stored in this groundwater, probably about 2,000 millimeters if we convert this to moisture content in terms of effective rainfall stored within the catchment drift material. The soils are also very retentive of water as well. A couple of meters of peat will have over 1.5 meters of rainfall equivalent stored in it. So we've got high storage to damp tracer signals. So having this information about the perceptual model of how the catchment functions, we've got our isotope data, which tells us how these kind of different elements of the catchment landscape are influencing the flow paths of water through the catchment landscape. So if you have a data-rich time series of isotope in rainfall, this is what it looks like. This is showing a couple of years' worth of data. You can see the hydroclimate of the catchment pretty well. As I say, about 1,000 millimeters of rainfall, generally evenly distributed throughout the year. Big events for us are events that are more than about 25 millimeters per day. So we only get about 3 or 4 of these a year typically. And most of the rainfall comes in really low intensity events of just a few millimeters. The catchment's pretty flashy when we get these bigger rainfall events, but it also responds to almost every tiny little rainfall input because these saturated wetlands are well connected. So each day's rainfall brings a different isotope signature into the catchment, which is a very useful tracer then for looking at the transformation of rainfall to runoff. There's a seasonality in the precipitation inputs. We tend to get precipitation that's depleted in the heavier isotopes during the winter periods, and it tends to be enriched in the heavier isotopes during the summer periods. This is shown deuterium, which varies from about 0 to minus 150 per mil in terms of its isotopic variability. But despite this seasonality, we see that the big day-to-day variability is quite marked, and that's because in Scotland we can get rainfall coming from the southwest or the northwest, which can bring very different isotopic signatures almost at any time of the year. Within the stream, you'll see that the variability, the scale is different here. So most of the stream variability can be described by about 20 per mil variation in deuterium. And the stream picks up the kind of seasonality much more clearly than the rainfall does because the water stored in the catchment modulates the tracer input. It mixes the tracer input and it kind of damps it down and lags it. But in certain events, where we get big events, we might see a rapid translation of a tracer signal through into the stream, which gives us information about the short-term dynamics of the runoff response in the catchment. So both this seasonality and this day-to-day variability can be really valuable information that we can incorporate into hydrological models. So in terms of thinking about conceptual models in the catchment, we tried a range of different model configurations using single, 2, 3 different types of conceptual storages linked together in different ways. And we found that these were unsuccessful unless we could conceptualize within the model the dynamics of this saturated area. The catchment's got a pretty flashy response, and it really depends on how much this saturated area is expanded. So Christian Burkle, when he did his PhD about 8 or 9 years ago, he went out about 7 or 8 times and mapped the extent of saturation with a GPS several times under both dry conditions and wet conditions. And he was able to model the variability of the saturation extent in terms of a fraction of the catchment coverage on the basis of an antecedent precipitation index, the evaporation on a day-to-day basis, and a simple kind of soil water storage parameter. So we had an algorithm for predicting the extent of the saturated area, which was crucial to any subsequent modeling. So after trying various different model configurations, we settled on a relatively simple 3-storage model structure. So we were just using a conceptual model in the first instance. And basically, we've got storages to represent the dynamic saturation area. We've got a storage to represent the steeper sloping hill slopes. And we've got a storage to represent the deeper groundwater box within the catchment. Now, with modeling, with a trace-rated model like this, we're routing not just precipitation through the catchment, but we're also routing the traces through these different storages. So essentially, the key thing in terms of capturing the catchment's hydrological response is to be able to partition the rainfall inputs between the saturation area and the hill slopes on the basis of the algorithm that I just described. And then that allows water to be routed either directly from the saturated area to the stream channel. If the catchment gets wet, this hill slope store can spill into the saturation area, or it can also recharge a groundwater store that also transmits water to the stream. So it's a very simple model configuration. The model's relatively low parameterized. There's 5 parameters generating the runoff response of the catchment. But in addition, we need 3 parameters, which we have as mixing volumes in each of the store, which allows the tracer signal to be damped. And these parameters we calibrate using a kind of sorting algorithm to go through about, I think it goes through 50,000 iterations and retains the 500 best parameter sets. And all of the parameters end up being reasonably well constrained and identifiable. But a key thing to note is to simulate the kind of hydrological response of the catchment, we need dynamic storage, which only varies by about 150 millimeters per year. To damp the tracer signals, we need mixing volumes which total a few thousand millimeters of storage. And that's really key to resolving this paradox that Jeff and Keith talked about between the celerity of the runoff response through the dynamic storage and the slow velocity of the water molecules or tracers through these longer mixing processes and flow paths that we get at the catchment scale. So when we've got a model like this, we need to calibrate the model on dual criteria using both flow data and tracer data. So we basically are getting the model to try and optimize a performance statistic both for discharge and for stream isotopes and weight these evenly. And when we do this, the model works pretty well for both. We get reasonable simulation of the stream hydrograph. This is looking over about 5 years' worth of record. And we get reasonable simulation of the tracer response as well. So we can be reasonably confident that we're getting a reasonable representation of both the runoff response processes in the catchment at a lumped scale and the mixing processes that are going on. The model's not perfect, obviously. It struggles most during the driest conditions, trying to simulate the re-wetting, as most hydrological models do. And also during summer periods, we tend to underpredict the stream isotope signal, because we get fractionation in the valley bottom wetlands, and that's difficult to capture in the models. But in general, the model does a reasonable job. And by using the 500 best parameter sets, we can get the uncertainty estimates around the predictions and the parameter values as well. So just to show other ways in which we can use isotopes as being diagnostic of the models, on the red line here, we've got the simulated isotope signature over a few years of the storages in the groundwater store, in the riparian peatland store, and in the hill slope soil water store. Now, this is just a kind of soft qualitative validation or test of the model, because we're basically comparing measurements taken in one lysimeter or a couple of lysimeters with a kind of a catchment scale conceptual storage. But basically, the groundwater in the catchment is incredibly constant and well mixed, both in terms of measurements and how the model deals with it, because it's a big store of water of over 1,000 millimeters. Within the riparian peatlands, the model does a pretty good, it underpredicts during these fractionation periods that we get during the summer, but generally it's in the right range and is heading in the right direction compared to what we measure in the peaty soils. And the hill slope storage is a bit more difficult, because effectively that's dominated by drainage from the deeper soil profile during dry conditions and then the upper soil profile during wet conditions. And generally it's kind of doing that. It's heading in the direction of the upper soil profile when it gets wet. So it's by no means a perfect validation of the model, but it gives us reasonable confidence that we're in the right kind of range of mixing relationships and we're getting a kind of similarity of response that fits the runoff. In addition, we can look at the dynamic storage changes in the landscape units, and I should say that we've got uncertainty estimates around these, which are relatively large or significant, but I've left them out for the sake of clarity here. But this basically shows the storage change within the saturated area, which is very small because that's always spilling. It's always producing a runoff response. On the hill slope store in the blue here, that is usually not spilling, but in really wet periods, it connects and spills into the riparian area. And then when it dries, it disconnects, and we get moisture deficits forming in this particular storage. And then in the groundwater store, that tends to increase during wet periods and then draw down as the hill slope store becomes disconnected. So we can visualize the storage changes in these main landscape components. As I said, though, the storage dynamics in terms of the dynamic storage change are in the order of magnitude of 100 millimeters. For the tracer damping, we need to be invoking thousands of millimeters of storage. And we can see how this varies in relation to the runoff response on the bottom slide there. So another thing that we can do if we're looking at the mixing and storage changes and fluxes from individual catchment units or individual storage units is we can estimate what the age of that water is by basically putting a flux tracking algorithm within the model that follows the tracer through in terms of time stamping inputs and then mixing them with stored water, and we can get a measurement or an estimate of the stream water age across the hydrograph over a few years. And basically, with uncertainties of kind of around about 30 to 40%, especially at kind of higher flows, we can see that the model's toggling backwards and forwards between ages of a few months during really high flows, and then during low flows, it's going to the order of a few years. And that's when the groundwater stores are dominating stream runoff during low flow periods, and then during high flow periods, obviously the saturated areas are well connected. The ages are still relative, even for this young water, the ages are relatively high because there's a lot of water stored in the surface peat. So you get relatively low new water contributions on a day-to-day basis. Typically, old water constitutes about 90% of the hydrograph, even in big events in this catchment. And we can view this as a mix. We can track the age of the water in the groundwater store, which is, as I say, is a few years. We can look at the saturation overland flow going from a few days to a few months, depending on what the wetness conditions are. And then we can see the young ages of the hill slope water when that fills, spills, and connects with the riparian wetland. So we can see how the age distribution of water in the stream is composed of the different component parts of the catchment. And we can estimate the kind of average stream water age, which is about 1.5 years over this time period of record. And then we can then go further with this in terms of looking at cumulative frequency distributions of the travel time distributions of the different water sources in this kind of way. So again, the older groundwater, the stream water tending to that at low flows, and then going towards the kind of saturation overland flow from the valley bottom wetlands during high flows. We can also get quite crude estimates of the ages of evaporated water from the hill slope and saturation area, which tend to be quite young. But these are just an artifact of how that's parameterized within the model as a storage term in the soil moisture store, rather than anything that's really reflecting any physical processes of transpiration. They're not represented in these models, but I'll say a little bit more about that later on. So that's great. We can understand from these models quite a lot about catchment processes. It tells us quite a bit about the flow paths, the mixing relationships, and so on. But it's still relatively unsatisfying in terms of it's quite a lumped representation of the catchment. So the subsequent development of the model that we developed and published in WRR last year has been led forward by Marilyn van Hoogevoort, who basically took a very similar kind of conceptual model architecture and then spatially distributed it at 100-meter grid squares across the catchment. So basically, we had a soil store, a groundwater store. We removed this kind of saturation area algorithm because that should then become something that's a kind of an emergent property of the model at the catchment scale. And we included some parameterization for vegetation and snowmelt effects because we wanted a more generic model that we can apply across different catchments, especially in northern regions. So then the input data for this model is then using a DEM based on a LiDAR survey, which gives us a much more accurate kind of topographic basis for the model. It gives us then algorithms for connecting the cells within the model architecture to look at how the mixing processes link together at a finer resolution. And we could also parameterize the model in a different way for the kind of valley bottom wetland areas shown in dark brown here, and the upper hill slopes in the pale brown. So we could build into the model this difference that we knew from the geophysical surveys and soil surveys in the riparian wetlands. And then we could also spatially distribute the vegetation effects in terms of the evapotranspiration going on at the catchment scale. And this is reported in a paper that Marilyn's just got coming out in HP. So the model, despite being, it's more complex. I think this has got 9 different parameters. 9 calibrated parameters. It was calibrated by Monte Carlo analysis, taking I think about 500,000 parameter sets and then reducing it down to the best 100. And that gives us uncertainty estimates. But with more parameters, unsurprisingly, we get a better simulation of the stream hydrograph and a better simulation of the isotope response. Again, it was calibrated against Nash-Sutcliffe efficiency values for both the isotope data and the runoff data. So it's a dual calibration again. The model works particularly well when we get to really wet periods. That's lacking a characterization of some of the newer water getting through to the stream. You can see it doesn't picture these variability, it doesn't capture this variability in the isotopes quite so well. And we also still get the problem of the underestimation of the isotope values during the summer where we get fractionation occurring. But it's progress in terms of improving the simulations. But the nicer thing about then having the more spatially distributed model like this is then we can interrogate the model in a spatially distributed way in terms of looking at the catchment, sort of into the catchment orthogonally here, and look at the temporal dynamics of the runoff fluxes from the different cells and the ages of water that's coming out of those different cells. So having the flux tracking routines within the model allows us to estimate the water ages. So I'm just going to run an animation now that runs through a kind of a 12-month period, going from the wet winter period through a dry summer into another wet winter period. And typically, these are on logarithmic scales here. So dark blue is showing high water fluxes. So here it's highest in the valley bottoms, aggregating along the flow lines as you'd expect. And we see the mixing between the younger water that's coming off the hill slopes, that's where the storage is relatively low, and this younger water then spills into these valley bottom areas where the water ages are relatively high because the cells are having the influence of groundwater and mixing of peaty water in the valley bottom areas. But if we just run through the animation here, it hopefully becomes clear, as you can see, that when the catchment wets up, the fluxes on the left all become high. The ages of the water age down the hill slope. And then as the catchment dries up, the fluxes from the upper hill slopes reduce. The water ages begin to get older as it becomes more groundwater dominated. And we've got the catchment kind of, going through this kind of wetting and drying dynamic. So this helps us visualize much better the kind of mixing processes that are going on. As we go through into the summer period, you can see the catchment begins to dry out. The fluxes really drop off in all but the valley bottom areas. The water ages get really old. Many of the cells disconnect in the driest period. And then we see the catchment then going through into the autumn and then beginning to wet up again. So the runoff fluxes then begin to increase across the catchment. You'll see the left-hand figure go increasingly blue. And then we'll see the age getting younger as we go to the wetter periods, as the upper cells become dominated by near-surface runoff again, and the ages of the runoff become younger. So we can see the spatial variability, or visualize the spatial variability of the processes much better using these kind of spatially distributed models. In addition to that, though, we are aware that there are a better modeling kind of tools available now for more spatially distributed conceptualizations of the processes that are going on. So our current efforts with tracer-aided models are really now taking some of the more physically based models like hydrogeosphere and trying to calibrate those in a way that keeps the models relatively simple but gets us a better understanding of the spatial interactions of the processes going on. So Pertti Ala-aho has been carrying this work forward, and he's basically parameterized hydrogeosphere. So we've got the saturated area in the valley bottoms. We've used our soil maps and our geophysical data to map the depth to bedrock. So we've got a kind of architecture in the model reflecting the distribution of soils and drift materials at the catchment scale. And obviously these depths of drift are really important in terms of groundwater. But the model parameterization is relatively simple. We basically have a layer representing the riparian peat, which is mainly a kind of overland flow domain that's regulated by some rill storage and a Manning's N in terms of the algorithms. And then we've also got the kind of drift, where we've got a porous media domain that's dominated by the saturated hydraulic conductivity and anisotropy of the drift material. And then we also have a domain representing the evapotranspiration interception storage. So we've tried to go for a very simple physically based model. We've got 12 parameters here. It's calibrated in a PEST framework using a cluster to carry out the very demanding calibration process. But it's been pretty good. We've been able to calibrate the model against stream flow, measured stream discharge, and also the distribution of groundwater levels measured in the catchment by wells. And again, within this, it gives us a really powerful visualization tool. So if now we're up the top end of the catchment looking down, you can see the saturated wetland areas in pale here in terms of where they're parameterized in the model. And then this, again, gives us a really nice tool for visualization. So what I'm going to show here is an animation through a 30-day period. And it shows, first of all, the kind of overland flow distribution in the catchment as we go from a dry period through a wet period event where there was about 80 millimeters of rain over a couple of days. The pink area shows the saturation extent. The black-blue areas show the surface flow velocities. So you can see the stream channels, and you can see the patches of overland flow that at the dry period are generated by groundwater seepage. So again, looking at this in terms of the visualization of the processes as we move through the initial dry period, the saturation extent begins to decrease slightly, the overland flow decreases a little bit, and then we get an initial wetting and expansion, and then we move into the main wet period in the catchment where we see a big extent of the overland flow domain, higher runoff velocities, and then a contraction again as we move through into the subsequent dry periods. So it helps us at a finer resolution get an understanding of the spatial patterns of the processes that are probably going on. More of a sort of steady state realization is the groundwater exfiltration that the model's predicting, which is basically in the areas where the overland flow is occurring, because the groundwater exfiltration is feeding that overland flow. But basically, this is a much more steady state kind of picture in the catchment of the saturation area, the edges of the saturation area being areas where we've got groundwater exfiltration going on. And as we move through the wet period, this expands a bit, particularly on the upper hill slopes where we've got more limited storage, but it's a much more kind of static pattern. So the value of having this kind of information is it tells us about how the model's visualizing the flow paths, the storages, and the mixing processes. And the work that we are next trying to do is to try and compare this with spatial surveys that we've undertaken within the catchment, where we've done repeated surveys of over 100 sampling points in the riparian wetlands, and we've done multi-tracer analysis, and we've been able to classify waters as being groundwater discharge areas that are generally depleted in isotopes, low in DOC and high in alkalinity, with soil water areas that have more enriched isotopes, high DOC and low alkalinity. And so we're going to use some of the solute transport code within hydrogeosphere to see to what degree these patterns are reproduced on days where we've got high quality tracer data. But that's very much work that's currently in process. So we've been working in these kind of headwater catchments in the Scottish Highlands for quite a long time. And it's a fair comment that we maybe need to get out a little bit more from these kind of nice mountainous areas and also engage in some sort of more practical problems. One of the reasons that there's not been so much uptake of tracer-based modeling, I think, by the wider community has been a kind of an assumption that it can only really be used in research-intensive basins where we've got very rich data sets. So over the last few years, we've been working in another small catchment, about 8 square kilometres, which is on the edge of the town of Banchory, which is undergoing rapid urban expansion, like most towns are in most countries. And one of the things that we wanted to look at was, could we use the isotopes as being predictors of different types of urban impacts on water ages and mixing and storages within the urbanizing areas and the non-urban areas? So within this catchment, we measured flows and sampled isotopes at the catchment outfall. But we also had a stream that was draining a non-urban area and a couple of sites that were draining areas with different degrees of urbanization. So we've collected several years' worth of isotope samples, particularly sort of biased towards high-flow events. And we're in the lowlands here, so it's a much less flashy hydrological regime. The events tend to be more muted. But the biggest isotopic variability is always shown by the urban stream, which is the black dot here, and that always tends to be the outlier because it's representing the immediate transformation of the tracer signal in the rainfall through the urban drainage system from impermeable surfaces into the stream channel. And at these times, the catchment outlet is basically dominated by this urban runoff response. In bigger events, the rural subcatchment becomes more influential as well, and that moves towards the kind of urban isotope response. So we've got similar kind of combined tracer flow data sets that we can then use within similar types of tracer-aided models. So we just have simple models of a nonlinear soil store, a linear groundwater store for the rural area, and then we can add another component from the urban runoff. And here we have mixing volumes in the soil and groundwater store, but we don't put a mixing volume in the urban runoff store. So we just allow that to go straight through into the stream channel. And these models, like the ones that we've got for the headwater catchment, they do a pretty good job too. In the urban stream, a lot of the variability is picked up by the model pretty convincingly. In the rural stream, it's a little bit less convincing because the rural stream is much less dynamic and variable. And we also get a kind of constant groundwater discharge during the summer period that sort of fails to pick up little events or some fractionation that we get in some small wetlands within that catchment. But by the time it wets up again, it's doing a pretty good job. And in the catchment outlet, it really captures the variability pretty well also. And the beauty of having this kind of information is then we can look at the travel time distributions of different urban waters. So if we look at a storm control measure in a newly urbanized area, unsurprisingly, the ages of water there are basically typically in the order of a few days. It's very responsive and then gets a little bit of slow drainage that is a little bit older. In the rural area, in contrast, we get some kind of younger water that's of the age of about 6 months in bigger rainfall events, but most of the water will come to be, we get a secondary peak at an age of over a year where we get the kind of more persistent groundwater response of the rural areas. And then in an urban subcatchment, we're kind of, to some degree, combining the effects of the paved surfaces with kind of gardens and other open spaces. So it's skewed towards the younger waters in the age of a month or two, but then it kind of flattens off and it's got much less older water because of the urban storm routing. And then at the catchment outlet, effectively, we're kind of integrating the urban and rural responses together, or the models integrating those together. And we can see these in the cumulative distribution frequencies of the different water ages. So we're going from average ages of about 10 days to about 6 months to about 2 years to about a year or so in these different responses. And this is really potentially really useful in terms of helping the design of green infrastructure, in terms of what storage areas, storage ponds you would need to retain water for certain time periods if you're wanting to retain certain types of pollutants that might be coming from urban areas, or the kind of storages that you might need for kind of green roofing techniques to damp down the tracer signal. So there's a lot of potential, I think, in using these tracer models in applied type landscapes. So just to wrap up then, hopefully I've been able to show you that tracer-aided models are a kind of an underutilized but very powerful tool in hydrology. The approach is maturing, but it's got a lot of applications that still could be made. Having high-resolution tracer data and increasing computer power usually improves the understanding and visualization of the processes that are going on. And we really need to put a lot of effort now into ground truthing what the models are showing and upscaling to bigger catchment scales, integrating things like vegetation and evaporation effects, and going beyond our kind of humid temperate basins where we tend to have most of our experimental sites to applied sites like the urban catchment that I showed the example of. And with that, I'd like to thank you for your attention, and I'd be happy to take any questions that anybody would have.
Thanks very much, Chris. Great talk, great visuals. Okay, questions from the audience?
First of all, thank you very much for the presentation. It was really, really interesting. The first question is regarding the exfiltration simulations. Does your model, you used hydrosphere, right? So does it also compute the infiltration, so the change between infiltration and exfiltration over time, if there is any variation in these dynamics? And the second question is, how would you go about validating that? Could you use did you see any change in the tracer signal the in-stream tracer signal due to that exfiltration?
Yeah. So so the model has got is temporally variable in terms of the infiltration and the real storage that's going on a day-to-day basis. It's keeping account of the water fluxes. We can sort of visually validate the model in terms of where we know that we've got groundwater seepage areas within the catchment. We've got a PhD student who's been doing some more focused work in some of these areas of groundwater exfiltration to measure groundwater levels and the time periods where we've got overland flow. So not at the catchment scale, but in a few restricted areas, we're going to be able to test the validity of the model. And in terms of predicting the kind of tracer movement within the model, that's something that we're just starting to do. We're working with some of the groups who've been involved in the development of hydrogeosphere to look at their solute transport code, to use the particle tracking for different tracers to see how we can best fit that into the into the structure of hydrogeosphere. So that's still work in progress in terms of how we're doing that. But in terms of the sort of physical representation, we're reasonably happy. We've got a reasonable representation of what's going on.
Andrew.
Hi. So when you're looking at calibrating with traces as well as flow, there's two potential benefits, I guess. One is that you would constrain the parameter space, but the other would be that you would actually constrain your uncertainty of your predictions. Have you looked at the latter?
Yeah, in a number of different ways. So and in different catchments, you see different things. So in some catchments, you will get, if you calibrate purely on flow, you'll get better flow simulations and perhaps significantly worse tracer simulations. But you might not. In some cases, that doesn't necessarily happen, and vice versa. Generally, if you're calibrating on isotopes, the flows will be degraded much more than what the isotopes are usually, because they're a lot more sensitive. But in general, in terms of constraining the uncertainty of the predictions, I don't think, I think in general the uncertainty bounds that we get are pretty similar whether we're using isotopes or dual traces. It's really getting the trade-off between getting a reasonable flow simulation and a tracer simulation. But I think it's one of those things that as we're getting more case studies of different catchments where we've got different data sets to do that, it's something that we've been having a discussion as a group about what to use as objective functions and to explore this issue in a bit more detail, really. Because in some situations we're using Nash Sutcliffe's, in some situations we're using like Kling-Gupta efficiency statistics, and they give different results. It largely depends how variable the isotope response is in relation to the stream water response. So there's a lot of open questions in that still that we need to address.
Okay. Just, can I follow up?
Yeah.
Maybe I don't quite get the big picture benefit then of using isotopes in this way.
In terms of the bigger picture benefit?
Yeah, like what's the big benefit to doing this?
The big benefit is it's telling you, it's giving you a much more insightful perspective on what the total amount of water storage is in the catchment that is hydrologically active in terms of damping a tracer signal. So it goes back to the initial slides of the Colin Neal study, that if you're just interested in simulating a hydrograph in a catchment like these, you can do that with about 100 millimeters of dynamic storage change. If you just use that storage for damping the isotope, then you won't see any damping. You'll just get the rainfall signal coming in and coming back out. So if you were going to then use that model in a way to, say, simulate a water quality parameter, the model would be useless to do that. And I haven't talked about it today, but the lumped conceptual model, we've done a couple of papers simulating DOC in the stream as a lumped DOC model that's basically using the tracer-aided model to provide us with the kind of storage dynamics, and that can be used in a hydrochemical model. And it would be similar if you were trying to simulate the effects of land use change, and the distribution of storages within the catchment would be perhaps sensitive to that. But in all that, if you're just wanting to predict a kind of 100-year maximum flood, you don't need any of that information. There's lots of applications where you don't need it, but there's a lot where you do.
So in theory, the objective functions defined on flows and the objective functions defined on isotopes should not be conflicting, right? And if they are, that means there is some shortcomings in the model.
Yeah. So we don't use different objective functions for flows and isotopes. We use the same objective function, and we weight them equally in terms of model applications that we've done. But there could be various reasons why you wouldn't necessarily want to do that. If you had if you were happy with just a reasonable simulation of the isotopes, but you really wanted to get the flow more accurate, then you could, weight more heavily the calibration on the flows.
So my interpretation is that when you add isotope information to your model, if it degrades the performance of flows, you might need to revise a little bit your mass balance, I don't know, representation in the model as well. So it can tell you a lot, really.
Yeah.
Okay, Jeff.
So Chris, I really enjoyed your talk. The animations with the groundwater piece were quite impressive. And of course, looking at that photo, they were focused on spatial patterns at the surface in terms of where groundwater is exfiltrating. What's your vision for how we forge better links to the groundwater community? Because I guess, looking at a landscape like that, your near-surface geophysics gets you down some meters or maybe some few tens of meters, perhaps. But you imagine the deep flow paths and returns of water in a valley system like that in the larger D catchment where you're working. And all of that seems so sensitive to how you're defining that bottom boundary. And you didn't show kind of the flow nets, if you like, how they develop through a landscape. But I guess I'm wondering how we make that connection to regional hydrogeology and maybe the more traditional applications of hydrogeosphere in terms of, deeper unconfined and confined aquifer units. How should we be thinking of that going forward in our catchment studies?
Yeah, these are probably not best environments to kind of demonstrate that, because I think the drift kind of hydrogeology here is so dominant that it basically decouples the bedrock groundwater, certainly in the valley bottoms, from the river channel network. It's less a case maybe up on the steeper hill slopes. But I think in other countries they've been more successful in doing that. I mean, Pertti, who's the postdoc who's working with our group, in Finland, they've got some really neat studies where they're looking at river-lake groundwater interactions. And they've mobilized, good interdisciplinary teams to look at, drilling deep wells, using thermal imagery to find groundwater discharges into streams, and get that kind of landscape scale influence in terms of the groundwater flow paths. But it's a big challenge. We tend to publish in different journals, or if we publish in the same journal like WRR, it's different readerships of papers. And probably we maybe need some initiatives, Chapman conferences, that kind of thing, to really try and bring the two communities together better. And maybe getting some test sites where we've got good quality kind of isotope, near surface, deeper kind of hydrogeological information. But I think also the revolution in sort of hydrogeophysics over the last 5 to 10 years is probably going to help in that direction, because I think hitherto the expense and the difficulty of drilling boreholes, certainly in the days before Chris had his more kind of mobile rigs, really precluded doing a lot of deeper drilling in catchments like this. But I think the ability of a lot of the hydrogeophysical tools to be able to provide more rapid appraisals of bigger kind of scale impressions of what the subsurface architecture is like and how that's influencing things really provides a new tool that will help drive that collaboration, I think.
Hey, Ali, yeah, quick, please.
Thanks, Chris. Andrew asked my first question. The second question, within those 9 parameters you consider for your model, did you consider any mixing approach parameter, like a storage selection function, or it's just storage?
No, it's effectively, so that within each model cell, the assumption is that the mixing is complete and the water comes into the cell. But effectively, because it's distributed in terms of the connectivity of the different cells at the catchment scale, it's giving you a partial mixing mechanism. So both within the lumped modeling approach and the spatially distributed modeling approach. But we've been doing some work with Andre Ronaldo and Gianluca Botta, Paolo Benettin, and they've for the Brundtland Burn catchments, they've for our daily isotope tracer time series, they've carried out a storage selection function approach, and it basically gives a very similar kind of result. The only difference is that they're kind of the older water age that the storage selection function estimates is in the order of about 1.5 to 2 years. But the median younger water fraction is very similar from the two approaches. And probably the main reason for that difference is that because we're dual calibrating with a runoff model, we need to invoke that bigger groundwater store to simulate the low flow conditions within the catchment, whereas in the storage selection function, they don't need that. But they both identify the deeper store as being the most ill-defined and uncertain part of the system.
So you mean the uncertainty of the Gianluca-Butter approach is less than the original conceptual model you developed, right?
No, I wouldn't necessarily say, well, in terms of just looking purely at the tracer response.
Yeah, tracer response.
But that doesn't have any hydrological component to their model.
Yeah, and follow-up, very quick questions. What was the simulated mean transit time in those figures you shown about the water age?
In terms of the...
you had a tracer simulated water age 10 years, 15 years. I'm curious about the mean transit time of the system.
Of the system was about 18 months. 18 months? Yeah.
Okay, so this conceptual model, in my opinion, is more semi-distributed compared to the very lumped approach. We had the problem of old water delineation with lump approach that using isotopic tracers that there are lots of literature on that they cannot capture more than 4 years mean transit time and something. Did you have also this problem in this more distributed approach you developed?
No, let me jump in. We are over time. I mean, this conversation and Q&A can continue in Alexander. So we're headed to Alexander for a drink.
Sure.
And everybody's welcome. And Ali, please come over, and then we continue there. Okay. Thanks, Chris, very much for coming. Great talk. And